today I would like to present my lecture according to our syllabus entitled mass transfer. Okay, what is the mass transfer? The mass transfer is the movement of something that have a mass. It means anything which have mass, we call it as a, and they are moved, we call it as a mass transfer. It's involved the process of diffusion and also the convections. In biosensor, actually we call it as a mass transfer. In biosensor, we define as a rate of reactions and diffusion of electron on the biosensor surface that correlates to the change of light on the surface. Receptor-based biosensor actually is the output signal given by this type of biosensor. It depends on the number of receptor molecules which have bound to the analyte or molecules. We call it this between the bioreceptor and also the analyte as an affinity binding. Okay. However, the rate of which the binding occurs will affect the responsible times, the response times of the sensor itself. So they have two rates to consider in biosensor actually. One is the rates to which the binding reaction take place. We call it a reaction rate. The number two is the rate at which the analyte diffuse to the receptor on the surface. We call it a diffusion rate. When the reaction rate is very fast compared with the diffusion rate, hence the biosensor will be operating in a diffusion limited modes. The rate of binding is proportional to the product of the concentration under each particles. We call it a collision theory. Thus, at low concentration of antigen, the reaction is low. And biosensor often required to detect very small concentration of antigens. There may have be a compromise between the response time and also the sensitivity limit. When an antibody is immobilized in the active site, the rate of the binding reaction is often diffusion control. We call it as a mass transfer limited. The rate of filing binding site will be proportional to the number of unbound sites. This must be the case at the start when no sites are occupied. The binding has to be fast, and at the other extreme, when all the sites are occupied, the rate of binding must be zero. The higher the concentration of the analyte, target analyte, the more likely will there be a binding reaction. So for the analyte must contact to the receptor to promote the binding reaction. Means in this case, a high concentration of analytes molecule will increase the number of collisions between the antibody. In this case, is as a receptor and also the analyte. We have first order kinetic, so you can refer to the slide. So the rate of binding will be proportional to the analyte concentration and the number of free sites still available on the sensor of the surface. Mean the free site from the biomarker itself. Okay, so to the binding. So when NO is the total surface of the concentration of receptor, and is the surface concentration of receptor occupied by the analyte. Okay, so means they have different between the occupied by the analyte, so the concentration, surface concentration of the receptor itself before and after. K1 is the first order rate constant. C5, Cs is the concentration of antigen at the surface, and in this case the NDT divided by dt is the rate of the binding. So this is the you can see the initial rate of the binding when all sites are free will be controlled by the concentration of analyte at the surface of the sensor. The presents a problem. If we want our biosensor to measure low concentration of analyte, have a very low limit of detection, then equation 1 tells us that the rate of binding of analyte to the immobilized antibody on the surface of receptor will be slow. It may be necessary to allow allow a long reaction times for the sensor to reach a steady state signal where sensor had been incubated for hours rather than minutes to get a steady state response. So the incubation time in this case is very important to make sure the binding, affinity binding between the analyte and also the bioreceptor will be occupied. So before it comes to steady state response.